Welcome to today's Tech Talk. We are very pleased to have Professor Tim Bell from the Computer Science Department of the University of Canterbury in Christchurch, New Zealand. Tim's research interests include data compression, computer science for children, which he'll be talking to us about today, and computers and music. Tim recently completed, I think this is your last leg of your tour, a worldwide tour, talking about his project Computer Science Unplugged. This is a project that seeks to teach principles of computer science without using computers. So that is what we'll hear about today. Please join me in welcoming Tim Bell.
Well, yep. Okay, well, thank you very much. What I'm going to do today is just very quickly run over some of the ideas that we've been working on with this Unplugged project. I thought I'll start with a demonstration just to give you an idea. Also, I guess we've mainly got engineers here today. Any sort of non-programming kind of people here today? One or two? Okay. I'll probably be going fairly quickly over some of the technical concepts, whereas normally if I'm presenting this to people who aren't engineers, we'd probably spend literally 3 times as long on some of the concepts and dig into them a bit deeper. But since you'll be familiar with a lot of them, we'll go a little bit faster. And it's all in the book, okay? So you need 3 more, right. Okay, so Greg's been helping me out here with these black and white squares, which will be familiar to a lot of us as representing the binary digit or the bit, the fundamental unit of everything that's stored on a computer. And when presenting this to young kids or even the general public, I quite often start off with this demonstration where I've had Greg put up a random mixture of these binary digits or bits, and I'm just going to add some extra ones to make it harder. And what we're going to do is a bit of a, hopefully, impressive magic trick with it. Running out of bits. Get some more here. Black one there. Put a white one there. Okay, now actually what I'm going to get now, Greg, is to simulate something going wrong on this digital data, so it could be a CD with a scratch landing on it, by flipping over one of the bits. Okay, so if you just choose any bit and flip it over for me. Yep. Okay, you can try this at home. You can do it with coins or cards or anything that's got 2 sides. So have we got one flipped over? Just one. Okay, keep track of which one's flipped over. Just one. Yeah, one flipped over once, that's right. And my job as a computer scientist is to try and put this thing right. So I think the one that you flipped over might in fact have been that one there. It was, okay, thank you very much. And so how was it done? Parity, thank you. So Greg had put down most of these cards here, and I put down the extra parity ones to make sure that the number of white in each row was an even number. Okay, so there's 3 there, make it white to make it up to an even number. There's 4 there, so I'll leave that black because 4 is an even number. And down here, same with the columns, 3 there, so need another white to make it an even number. 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, so we need a white one there. And by the way, if you are trying it at home, that bottom corner one will be correct for both the check row and the check column. So that's a good little check that while you're sort of talking and things, you haven't got one of them wrong, or at least, unless you've got 2 of them wrong. And that can be done with any size, obviously, and you can do it with coins or cups or whatever's to hand. But the whole point of this Unplugged thing is we take a concept like parity and we turn it into something that's kind of fun. Maybe it's big like that, or you do it on table with cards. And then typically would be able to start reasoning about it with kids. So what happens beyond this? What would happen if he had flipped over 2 of them? Okay, and kids pretty soon work out that if you'd flipped over 2, you can't be sure exactly which pair had been flipped over. So if I say, if Greg had flipped over those 2 there, then the fact that there's an odd number in each row, in those rows and those rows, tells me that there's something wrong there and something wrong across there, but it could have been those 2 or it could have been those 2. Whereas when you flip over 1, there's 1 row and 1 column that's got an odd number of white cards in it, and so therefore that identifies exactly which one was flipped over. Incidentally, one nice trick with magic tricks, you explain it to the audience, and then you take it one step further. And so typically I'd then get a kid to flip over too, and I sometimes have an assistant, and the assistant will say, oh, it's ready now, Tim, or it's ready now, okay? And whether or not they use my name is a one-bit code to say whether it's the top right-hand one or the top left-hand one, okay? And so then you can get the right two, and it leaves them with a bit of puzzling to do. I've had some long arguments with kids afterwards about how it might have been done for doing two. So that's just a warm-up to the general idea of what we're on about with this. And where it started, it sort of came from three things all happening at the same time. Oh yeah, we'll move this out of the way, thanks. So one was I was involved in some music education and trying to communicate some of the boring subjects to kids. My kid started school and they asked me to come and give a talk about computers, and if you bring along a computer, it's kind of a bit boring for the kids because they've seen computers and what's the big deal. And also we had a science centre setting up in town, and they were interested in displays and activities that would sort of show computer science to kids. But you can't just put in a computer running software that they probably use at home, so what do you do? And I started looking at how people popularise science topics, and a lot of people who are involved in popularisation of science would take a topic that might not be interesting. You know, you go into a class and say, today we're going to do statistics, and they might not be that interesting. But if you say, today we're going to do lotto, then suddenly it becomes a lot more interesting, which is just statistics with long odds, right? Or today we're going to do viruses, maybe not so interesting. But if you say, today we're going to do snot, then suddenly it's interesting. And there was one science festival I went to where there was a talk that had snot in the title, and all the 10 to 12-year-old boys were going along to it. I mean, what could be more interesting? It was actually just about viruses, but chemistry, how's that, you know, publicized? Generally using explosions, okay? And in fact, I'm worried that the next generation of chemists is probably going to be a bunch of pyromaniacs because they've been to all these demonstrations using explosions. With physics, pretty much the same, blowing things up, lightning, and all that sort of stuff. So we've got this environment where all these scientific things are being popularized with explosions and fancy things, but what do we do with computer science? And that's really where the Unplugged thing grew. And I met with a few other people who were thinking like this, and we've pulled ideas and tried them out over the years and gradually put them together into a bunch of things. So first of all, there is a bunch of about 20 activities that we've developed, which have all been tried and tested and work really well. And I'll show you a few of them so that, you know, next time you're asked to go and explain at someone's class or some sort of situation where the people aren't that interested in computers, you might be able to use some of these. There's also 2 books that we've developed, and one of them is a bit more technical. The other one is designed for elementary school teachers, that sort of age group and that sort of background. And they have all the handouts, and there's activities in them and follow-up and explanations about how all these things work. There's a show that we've developed, and generally this has been run in the middle of winter in New Zealand in June, and it's been sold out. Lots of people come along to it. I think actually when they see the computer science in the title, they think that we're going to show them how to stop, you know, their computer from crashing or something like that. But from the surveys, we find out that they actually get a lot out of it. There's a website, and I'll give the URL for that at the end. And a lot of these things are available directly on the website. There's a bunch of videos. In fact, why don't I just... So we're working on a new set of videos, but I'll just give you an idea of what we're on about with a video of another activity. This is available on video.google.com, the Computer Science Unplugged.
Welcome to Computer Science Unplugged.
Okay.
These are a series
we'll play that
of
out there.
activities designed to introduce children to some of
It's
the
just a 2-minute video. There's actually 3 videos there. We're hoping to make a whole series of them illustrating all of the activities. This particular one is not the one I was going to show, actually. Let's count the dots. Let's just skip to sorting networks. Okay, so it goes through and explains how a lot of the output you see on computers is sorted, whether it's sorted by name or age or arrival of an email date or page rank or whatever it is. But this is a parallel sorting algorithm, and what's happening here is we have this chart on the ground, and two children follow along the arrows, or the lines. When they meet, they compare their numbers, and there's, the smaller number goes out the left-hand line, the larger number goes out the right-hand line. And so this is a parallel sorting network. We get three comparisons happening at once. So it's sort of conveying the idea of parallelism, the idea that we want to get this as fat as possible, to get as much parallelism as possible, and they come out sorted, which is kind of fun, actually. Then we give them bigger numbers, and it makes it harder, and we can develop bigger sorting networks. When we did this video, I had a great idea at the end to you should throw them all up in the end, and then 3 seconds later I realized it wasn't such a great idea, but it made a good video. So with the sorting network, you can start talking to the kids about, okay, let's say we had to sort 8 things, what sort of sorting network would you have? Well, we start off with 3 and 2 and easier ones like that. And then you can talk about parallelism and how wide can it be? Why can't, if you've got 6 values being sorted, why can't it be more than 3 comparisons wide and all that sort of thing? All right. So we've got videos. We've actually done some outdoor events. This particular illustration here is maths in the park, a bit of knot theory in this particular case, which is not directly computer science, but in the background, that orange on the ground there is actually a sorting network as well. We had an event, public event, people could come along to the park and do math, and including a bit of computer science. That's the biggest sorting network I've done is 50, so if anyone ever does more than 50 people sorting, you can let me know and we'll put it up on the webpage. And we built a new building at our university not too long ago, and as part of the landscaping, we put in a computer science garden. So in this garden, you might notice that there are 7 bridges, and when I have a bunch of school kids come out and they're getting a bit rowdy in the classroom, we go outside and tell them to solve the 7 bridges problem, right? So they have to cross every bridge exactly once. And it can't be solved, so that usually gives me a good break from the kids while they run around trying to solve it. And then when they get suspicious and think it can't be solved, then we try and get them to, we'll prove it, And some of them actually manage to reason through, so the reason is that because the degree of the nodes, there's too many with an odd degree on it, right? And they don't use that language, but they manage to reason that you need to have an even number of bridges and things like that. At least some of them do. This is the show. That handsome dude there is Arnold the Wonder Parrot, actually. And Arnold turns out to be the star of the show. Small, fluffy animals will always upstage you. He only got in as a gag because of the parody trick, okay? But it turns out in all the surveys that they liked all sorts of things, but the one thing that almost everyone liked was Arnold the Wonder Parrot. The books that I've talked about, I've had a lot of people asked to translate them into their own language. And so, in fact, the Korean version of it has just come out. And you can order that off the web if you want. And there is 2 Chinese versions, traditional and simplified Chinese under production. And it's even a Swedish version underway. And in fact, there's actually about 10 languages that one or another person, I just got a request 3 days ago to do a Turkish translation. Fair enough. If you really want, there's actually an Uzbek translation underway. So I got an email from Uzbekistan where an aid agency was working with kids and they wanted to do computing in the schools, but there's no computers. And so this was great because they could do it without computers, but they wanted to translate it into Uzbek, so cool. So I've talked about the parity thing. Let me talk a bit about what the goals are, in case they're not obvious. So the first one is, I want to communicate to people what computer science really is, because I think a lot of the people, if you ask a bunch of, especially sort of 12-year-old, 13-year-old kids, this is where they're making decisions about what general career direction they want to take. If you ask them what a computer scientist does and so on, they generally talk about programming, they'll talk about perhaps working on your own, maybe working long hours and all that sort of thing. And while some of those things might be aspects of being a computer scientist for some people, a lot of it, of course, involves teamwork, logical thinking, and a whole lot of other skills. And sometimes people get counseled against doing computer science because they are good at working in teams and relating to people and so on. And we want to try and communicate a lot of those sort of ideas. We want to reach minority groups and disadvantaged groups. And I've talked about making it available for people who don't have access to computers, but also a really big minority in computer science, of course, is women. And generally, the kind of environment that is in schools for using computers is one that's probably doesn't always appeal to women, and yet a lot of these puzzles and interactive team games and that sort of stuff do, and the problem-solving kind of side of it does. So sort of, rather than saying you have to learn programming and then we might let you do computer science, it's like you can do some computer science, and by the way, if you want to do it on a computer, you might need to learn programming to do that. We obviously want to create interest in computer science, especially the demand for computer science graduates is increasing rapidly. The supply is decreasing rapidly, and I think a lot of companies are getting very worried about the supply and demand situation. We use it to promote our own courses. If we're invited to go to a school, then this gives us a tool to actually interact with kids. And especially want to try and influence decision makers, kids making decisions about their futures, but teachers and parents have a big influence. You know, the parents read the newspaper, they hear about job losses and outsourcing and things like that, and have an influence on their kids. And likewise, teachers, you know, they might say, well, you like working on your own and you don't like communicating with people and all that sort of stuff. Why don't you do computer science? And we really want to try and get the message across to some of those people that, in fact, maybe it involves more than just the hacking thing. And we have fun. Maybe that one should be first. In terms of who this is being, the audience that we're delivering this to, I talked about the family shows that are really popular, which is probably more entertainment than education, but you can do a lot of these things, and some of the kids will get something out of it, and others will just enjoy it, and that's okay. School classes, we can actually sit down and do exercises and do a more thorough job of looking at some of the concepts. School assemblies, we have large groups of kids together. Sometimes they get together once a week or something, and you might have 500 kids there. Some of these are quite good in the large. So a lot of these activities are very big and theatrical, and that makes them easy to deliver in that sort of situation. In New Zealand, at least, we have quite a strong movement called SeniorNet, which is senior citizens who have typically bought a computer so that they can send email to their grandchildren, and then they discover that they need computer support, and they get together and help each other with their computers. And generally, they're very capable people, but they're completely new to computers, and they get in people to give them talks and so on. And I've found that a lot of these illustrations are very useful in the talks. They go down very well. And it's even been used in a trial. In fact, one of the methods, so data compression is an area that I've worked on, and one case where I was an expert witness, there was a method that involved LZ coding, and at the time, when there was this multi-million dollar lawsuit going on, my son was writing out a story, and he got a bit lazy, and instead of writing out a word, he would sort of find where he'd used the word before and put a little arrow pointing back at it. And I was sort of going to tell him off for it, and then I suddenly realized that in actual fact what he was doing was LZ compression. So what we've got here is bits of the text are missing, and to fill that one in, what I've done is I followed that arrow there to where it's occurred before. And so we can fill in all of that text just by following the arrows. And then here we've got a really big chunk of text, and you follow the arrow back to where it is, and you get a big chunk. And now the system has kind of learned that big chunk, and it can replace it like that. So zivlempel or LZ compression, sometimes it's called, it's used in zip, gzip, and ping and gif, and a whole lot of situations. But we can set up this worksheet for kids to work on, and then we can give them some text, and they can try and see how many things they can replace with where they've occurred before, and so on. Of course, the real LZ methods don't use arrows, they use two numbers, right? One says how far back the arrow points and how many characters it's pointing at. Somehow I've removed all the zeros from these slides. So let me just put them in fact. So it's 10 minutes and that's 30 minutes. So continuing with the theme there. So we have the show that is, can either be sort of a 10-minute science centre sort of show, where they say, at 3 o'clock this afternoon there'll be a show in the auditorium and we'll explain some concepts from computer science, through to about a 1-hour show, which is the one that we run as part of this Midwinter Festival. Usually more than about an hour. I find that no matter how much fun the kids are having, they tend to lose concentration after about that long. With all of these things, there's always a balance between entertainment and education level, and sometimes I think it's important not to get too hung up on trying to educate people about every fine detail, but let them just enjoy it and think through the concepts on their own. But generally I try and provide some sort of follow-up. There's follow-up material on the internet too. So for example, for the parity one that we did before, we were looking, that's basically a modulo 2 error correction checksum, okay? Just adding things up modulo 2. And then we can follow on to other error correction codes. So for example, ISBN numbers, the last digit of an ISBN number is a check digit. Does anyone know what modulus the check digit on ISBN is? 11, yeah, okay. So it's modulo 11, which means it's a number between 0 and 10. And if it's a 10, the digit that's used to represent it is an X. So in principle, 1 in every 11 of the books in your library will have an X as the check digit, and that just means it's the number 10. Okay? And we give the kids the formula for the check digit, and they can go through the library and check that they all add up. And what would happen if a digit was typed in incorrectly? What would happen if 2 of them were swapped around? And they can experiment with all of those sort of things. Now, another really important principle, I think, working with the kids is to get the answers from them. So, for example, with the parity thing there, I explained it as parity because most of this audience know what parity is. But with the kids, you'd sort of get them to count how many white squares there are. They'd figure out that it's an even number. They'd figure out that there's an odd number for themselves. And what I want to communicate there is that they probably are capable of figuring out these concepts from computer science for themselves. And if they can figure out that concept, maybe they'll go on to deal with some of the problems that we haven't solved. Because another problem with education, I think, is that because it has to be tested, we tend to have a science book that contains everything they need to know about science. They learn it all, and if they can get all that right, then they pass the test. But in actual fact, there's more in science that we don't know than what we do know, right? And the more we find out that we don't know. And it's the same in computer science. I mean, there's lots and lots of problems that we don't know how to solve optimally. There's lots of things that we're still trying to do, and that's what, I guess, keeps us computer scientists in business. But I think a lot of children and the general public would see that the main advances of computer science is can we get from 3 gigahertz machines to 6 gigahertz machines or something like that. So for example, MP completeness, right? One of the biggest questions in computer science, you can deal with quite easily because it's about exponential explosion, and that's kind of humorous, right? You can take a small problem like map coloring or a traveling salesman problem or something like that, and kids soon realize that these things are really intractable, that there's just too many things to try out, and they can work out how long it would take if you could do 1 million or 1 billion operations every second. And the whole infeasibility of these problems becomes a bit fairly obvious. And because they've solved problems like the parity one, we want them to try and think, well, maybe if they get their math right and they work on it, they'll be able to solve some of the other hard problems that we're trying to deal with as computer scientists. I'll just run through a couple of the activities that we've developed, just to give you a bit more of a feel for things. Binary numbers turns out to be a lot of fun, and I guess moderately simple concept, but very fundamental to everything that happens on computer science, because everything is just bits. And there's 2 main ways that I'd present it. One is getting a bunch of kids up the front of the class, in this photo here, and each one has a dot, or a number of dots on their card that is either visible or not visible. In fact, I use black and white cards because it corresponds to the black and white that we had on the parity. Okay, so one of my colleagues does this where each child holds the card, and they either have their hand up or their hand not up too, which means the audience can kind of read things off a bit more easily. But either way, you get these binary numbers. That's 10101 there. Now, to decode that binary number, you don't even need to be able to add. You just need to be able to count up to 21. Okay, there's 21 dots on the picture. And then we can reason with the kids like, well, is there another way that we could have done 21? That card with 16 dots on it, what if that wasn't showing, we can't possibly get 21, so we have to have the 16, and you kind of develop the greedy algorithm for converting it and so on. Incidentally, it's just giving out the cards is fun, right? So you give out the 1 card and then the 2 card and ask them what comes next. You know, the figure it out for yourself thing. Normally they'll say 3, put out the 4, no explanation, but then typically kids will either say 6 for the next one, 1, 2, 4, 6, and then they'll realize that no, 8 is the next thing in the pattern, and usually get up to about 1,024 before they kind of run out of steam. It can also just be done on a desk, so we give the kids a set of cards, and each one can play around with the cards and try and get the right number of dots showing. Just things that may be obvious to us, but is there more than one way to represent the number 5? Okay. What's the smallest number? Generally, they'll say 1, and then after a little moment's thought, they'll say 0. What's the largest number? The idea that the largest number is you double the biggest card and subtract 1. All those sort of patterns that come up with the powers of 2. What would the card be, if I put a card there on the table? How many dots? And typically they'll say, well, maybe it's 0 or maybe it's -1, and eventually someone will reason that it's actually got half a dot on it. So I've got a set of cards that have got a half dot and a quarter dot and so on, and can work with fractional binary numbers. Then moving from that onto my so-called ASCII code, we talk about how would you code these as characters, and again, kids will figure out for themselves that you should use a code something like that one there. And then I introduced the idea of modems communicating using beeps, and we use a low beep, beep for a 0 and a beep for a 1. Okay, so I'll send you a message. You guys should be able to figure this out. So left to right, here's the 1s and 0s. So that's beep is 0 and beep is 1. So beep, 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 beep. What letter? Yeah, H. Yeah, very good. And here's the next letter. Beep, 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 beep. I, okay? And that's my whole email message to you, okay? Hi. And then we can talk about how, modems actually go a little bit faster than that, and they make awful sounds and so on. I did it at one school, and the kids all went out into the playground afterwards and were communicating to each other like this, because it's actually it's a simple enough code that you can kind of memorize most of it or work it out in your head as you go along. It looked good too. Just while we're getting carried away with coding here, so base 1 coding, we can generalize from base 2 to base 1, okay, where each place is worth 1 times as much as the previous place. So here's the numbers 1, 2, 3, 4, 5 using just 1 digit. And where else is that used? Tally marks, counting on your fingers, the old telephones, and you go tick, 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 tick. And most important application of this coding, the annual use, the birthday cake. And in fact, one of my friends went to a birthday party where they had 100 candles on the cake, and you're probably aware that as you get more and more candles on the cake, it gets more and more dangerous because you kind of get this updraft from the flames. And this particular occasion, actually, the cake turned into a molten ball of wax and set light to the ceiling, and that was the end of the party. They had to get the fire brigade in. Computer science to the rescue. Each candle can either be lit or not lit, okay? So with 5 candles, what's the biggest number we can do? 31, okay? In fact, the song When I'm 64 is much more significant because that's when you need 1 extra candle on your birthday cake. Right? Also, fingers, instead of just counting up to 5 on one hand, each finger can be either up or down, right? So that's 1, 2, 3, 4. You've got to be careful with 4, 5, 7, 8, and so on. Actually, when I was in New York, I found out that the taxi drivers use a digital communication system. I was driving around New York, and they gave me guidance on what I should be doing using digital signals, usually the number 4. So, like, don't slow down for that orange light. That red light doesn't mean you should be stopping. Let's just keep moving here, and sort of messages like that. Okay, image compression. for this one, what we do, someone said this is me with a can of beer, but it's actually a spray paint can. Actually, I didn't bring a spray can with me today because I've just got off the aeroplane, but I was giving this talk a wee while ago, and I saw someone the previous night, and they asked if I wanted anything. I said, yep, I need a spray can for this and a packet of matches for the birthday cake. And they went into a gas station at 10 o'clock at night and asked for a can of spray paint and a packet of matches, which you try that if you want to have fun. What we do is, so here's Arnold again. Arnold always gets the feature in the show. So we look at how the image of Arnold is coded using pixels. We can talk about how pixels are just paint by numbers, and then it relates back to the bits. You know, the more bits you have, the more accuracy of the image you have, and so on. But this particular code here that I'm using is a run length code, and it's the one that's used in fax machines, and it's got the zeros missing again. I'll just put them in. There's a couple of key ones here. And what it represents is the first 4 means that we've got 4, so it's strictly black and white because it's a fax, 4 white pixels followed by 11 black pixels followed by 2 white pixels. And in fact, here's the image that I've started to do here. So we've got our 4 white pixels, 11 black, 2 white, and so on. And we've just got the last 3 lines left to do. And at this point, we pull out the spray can and have a giant inkjet printer and print pixels, in fact. So I have a little mask. Here it is, well used for spraying pixels through. Okay, if you're trying this at home, practice first because it's a wee bit fiddly to get nice even pixels, but it is possible. Now you could do that just using a PowerPoint presentation, but it's you know, there's a lot of drama when you get out the spray can and you get out and there's lots of fumes as well, by the way. But it's. And in fact, one of the things about all of these, in some ways, it's just kinesthetic computer science. It's actually just doing it with real things instead of a keyboard and a bunch of pixels on a screen. And I think for some learners, that's really important. Okay, some people like to hear it, some people like to read it, others like to actually experience it, and it can make it more memorable. That's the final picture, by the way, which if we zoom out, in fact, that's the original one that it was taken from. So it's a coffee cup, which of course is also very relevant to computer science, especially if we just put the little things above it. Okay, information theory or Shannon theory. So, like a challenge, how are we going to do this? Well, this is a retrofitted activity, and one of the things that turns out to be really good for this is the game of 20 questions, or basically, I'm going to give you yes/no answers. So I'm thinking of a number between 1 and 100. You can ask any question you want, but I'll give you a yes/no answer. So what question do you want to ask?
How many questions do we get?
You can have as many as you want, actually.
Is it greater than 50?
Okay, is it greater than 50? First question. The answer is no. Okay. Okay. Yeah. Okay. I'll put you out of it. It was 27, by the way. Okay, just, yeah. Okay. And I was doing this the other day, and someone said, is it less than 50? And I said, yes. And then someone else said, is it 100? Okay. And, well, exactly. Which actually is a great illustration of information theory, because what is the probability that I'm going to say no to that as the answer? 100%, right? You know that it's less than 50, so the answer to is it 100? 100% probability of that message. What's the information content? How much more do you know now that I've told you the answer? 0. 100% probability, 0 information. Okay, that's information theory. That's what it's about. It's the relationship between probability and information content. So, okay, here's another one. I'm thinking of a number. I'm not telling you anything about the range now. What question do you want to ask?
Is it an integer?
Is it an integer? Okay, it's an integer. It's a positive integer, I'll tell you that.
How many bits in its binary?
Yes or no?
A yes or no question.
I don't know.
Okay, so how many bits in its binary representation? But then you could guess each of those bits using yes or no questions, right? Yeah, okay. And which actually is equivalent to saying, is it less than 2, is it less than 4, is it less than 8, and so on, right? And that is actually quite a legitimate way of representing arbitrarily large numbers. And there are other ways of doing it too. Generally, after doing this, we can come down to looking at a decision tree. So if I tell you I've got a number between 0 and 7, then possibly the first question you would ask is it greater than or equal to 4? And suppose I was thinking of the number 5, I would end up saying yes, no, yes. 2 points to make here. First of all, the yes, no, yes is just the 101 that we were doing with binary before. Okay, so the path down the tree is the binary number. But the other one is that if you and I were identical twins, like we were computer programs that always did the same thing, because the same computer program will generally do the same thing, then I can anticipate what your question will be. And so I can just say, oh, the answers to your question was no, yes, yes. Okay? And that's how a lot of data compression systems work, is that they anticipate what the questions are going to be, and they just send out the answers to those questions. Now, this is a trivial sort of coding. We're saying that everything's equally likely. But suppose now we'll guess a sentence. So I'm thinking of a sentence. What's the first letter?
Is it Q?
Is it Q? No. It's not W.
Is it E?
It's not E.
S? Is it
Not S.
T?
T, thank you. Okay. That cost you 5 bits of information. Okay, 5 zeros and ones, or 5 yeses and nos. Okay, what's the next letter?
H-E.
H and then E. Oh, okay. Cost you 1 bit each to get that information. Okay, what's the next letter?
Space. White space.
Space? No.
R.
R, very good. Okay, 2 bits. Higher information content, okay, because there was a bit of surprise there, a lower probability. What's the next letter?
E.
E.
Space.
Space.
Space is not there.
This is just like working with the kids, actually. It's great, though. I mean, one of the things about working with kids, space isn't a letter, for those who didn't hear, is that they don't mind asking all sorts of questions, and they don't mind saying, but you told us something else before. And in fact, once or twice, we've actually discovered things that we hadn't thought of because, you know, the kids challenge you on stuff. One of my colleagues was doing something with cryptography where they were using envelopes and messages inside envelopes. And someone had, well, got it wrong, basically, and put the wrong things in the wrong envelopes. And it still worked. And afterwards, they looked at it and they realized that, in fact, the system that people have been using for cryptography didn't rely on the matching up to work exactly to still have a high strength of encryption. And so they published a paper about it. And that's one nice thing about working with kids. They don't mind asking questions. I appreciate that question too. What have we got? T-H-E-R-E space. What's the next character? I. Very good.
S.
Yes. Space.
A.
Not A.
N.
Not N. Oh, sorry, it is N. Yeah. Very good. Not used to people getting it that quickly. But we've got this idea that some letters have high information content, some have low, and so on. And one of the illustrations in the textbook is, you know, if you said, today I got a ride to school on a spaceship, low probability, high information content. Okay. And for those of us who are really interested, of course, we've got the negative logarithmic relationship between them. But I wouldn't normally get into that with elementary school kids. Okay. There's a lot of math and number stuff in there, but there's a lot more to computer science than that. And human-computer interaction, I think, is really an important area that we miss out on. And quite often I illustrate this with the Stroop effect from psychology. So I'm going to put up a word, and you just got to call out what color the word is written in. Okay, not the word, but the color that it's written in. Here we go.
Black.
That color's black. Okay. Or in New Zealand we call this black. Okay, just humor me here. Okay, next color.
Red. Blue. Red. Yellow. Green. Take off my glasses. Black.
Yeah, okay, he's got the idea. So you take your glasses off, it's actually a lot easier. Yeah, and so on. And we can talk about, well, what's this got to do with computers? And there's lots of examples where this comes up, but one that every kid's probably come across is if you've used Microsoft Windows, you're looking at the screen, what's written on the button that you press to stop the computer? Dell. Yeah, okay. And you know, who thought it was kind of strange that you press the start button to stop the computer? And most of them will say, everyone knows you press start to stop the computer, and you can point out the first thing under start is to shut down or log off or something like that. And that offers to start the computer and so on. Now that's not a big deal. People got used to it, and there's a kind of a cultural thing around it. But with almost any audience, you can generally say, has anyone here ever been frustrated by a computer? Has anyone ever found an error message that tells them not to do what they need to do, you know, that sort of thing? And, well, in fact, quite a safe one is, has anyone ever felt angry at their computer, okay? Violent thoughts towards their computer. This is my solution here, by the way, is the stop button. And you can discuss about, you know, this new interface would probably confuse people and that sort of thing. So here's a very familiar, if not outdated error message, which says, you know, it's either this problem or this problem. I'm not going to tell you which one. Okay, now let's have some fun here today. But I will tell you the solution, right? Replace the disk. And what happens if you replace the floppy disk? You get the same error message. Okay, it's like printer not working, check the printer cable and try again. Net result, printer not working, check the printer. And what you find is most people have learnt to disbelieve error messages, or as soon as it comes up, they click the OK or the cancel button or whatever, don't even bother reading it because they don't trust it. And it gets people thinking about interfaces, and perhaps the idea that we need to think a little bit more about the person using the interface. This is one of my favorites. So, yeah. Cannot delete the file, delete some files and try again, okay. And actually, I mean, you can talk about what actually might cause that kind of problem. Taking it unplugged away from the computer, so here's an illustration. This is a road in New Zealand. If you go across to our west coast, you come across this roundabout or rotary, and what you notice is someone's put a railway line right through the middle. And it really is a railway line going right through the middle of it. And as you approach the intersection, you notice that there's actually something like 14 signs, which really just says that bad design means you have to have lots of documentation, right? This is my favorite one. This is a road and a rail bridge shared. It's the road that have to give way, by the way. My favorite one's the sign for the cyclists. And, it's not all that backward in New Zealand, but we do have our fun bits of road. In terms of activities for kids, we've got a thing with designing doors and figuring out, you know, what the affordances are on the doors, and especially getting across to kids the idea that the system is the machine and the user. That, you know, rather than a really good system isn't just the box that goes really well, but it's this thing here, the user plus the machine, and therefore you have to understand this part of the system and how it works. And maybe we need people who know a little bit about psychology and sociology and teamwork and interaction and all that kind of thing to be designing the stuff that people are going to use, which is news to a lot of kids. Okay. I think, actually, that's probably, yeah, I'll just do sorting. So one of the activities with sorting, we have balance scales and a whole lot of weights that look identical. So the only way you can compare them is by balancing them, and of course that completely simulates the situation you've got on the computer with binary comparisons. It's pretty easy to get kids to figure out selection sort, you know, try and find the heaviest one and then put that aside, find the second heaviest one, put it aside, and so on. But you can even do quick sort, you know, just pick a weight at random and divide them in the smaller ones and the bigger ones, and then recursively deal with those. And we can talk about bozo sort, which, if you haven't come across it, it's basically mix them all up and find out if they're sorted. And if they're not, mix them all up and try again and see if they're sorted, which, of course, has exponential complexity and, well, takes a long time. Especially if you've got one kid trying to do it that way while someone else is using quicksort. Right, and I've shown you the sorting network. I think that's probably everything enough to give you a flavor of what the thing's on about. There's a whole bunch of activities there. And the goal of the project is just to make these available for people to use. So a lot of it's on our website. There's a book that's got a much more complete list. And we're just starting off a new project where we're going to have more videos and get lots of people contributing ideas for these. But we'll only put them up if they've been tested and we know that they actually work well. It's very easy to come up with things that don't quite work. And vice versa, actually. One of the activities that goes down incredibly well is one that's the storyline is there's a bunch of pirates offering a commuting service between these islands, okay, as they do. And they don't publish a map. So you go to an island and you have to say, I want to take ship A or ship B. And we actually have adults posted around the building or even around the premises, and the kids have to run up to an adult who's an island, and you say, I'll take B, and they say, well, you have to go over there. And they race over there and find out where they go. And after a while, they realize they should be drawing a map of this, and then they realize they should actually be labeling them with A's and B's because they get sent back to where they started and so on. And the goal is to get to Treasure Island. And eventually they get there, and the first one there wins and all that sort of thing. And then we can start talking about, well, what would happen if instead of islands and so on, I just represent the map with circles and arrows, and suppose that's the island that you start at, and I'm going to represent Treasure Island over here with a double circle, and we'll label the map like that, and we can start reasoning about what would actually get you to the Treasure Island, okay, otherwise known as the accepting state. And kids don't need to be too old. It generally takes a wee while, but they can figure out what it is. And then that, again, relates back to the parity thing, right? Because in this case, the Treasure Island means that there's an error. It identifies rows that have got an error if the A's and B's are blacks and whites, okay? But then in the book, we've got things like sentences that can be constructed by following around these finite state machines. And another exercise is interfaces. So we can get someone's digital watch with, say, 3 buttons on it, and we take it apart, basically. So your watch is showing the time, and if you press button A, then probably it'll be showing a stopwatch. Whoops. And if you press button A again, then maybe it's going to let you set the time. And if you press button B here, and what happens, and so on. And we put together this finite state machine that explains the interface on the watch. And generally, it's moderately complicated. And it helps them to understand that the interface isn't just a bunch of buttons and are we going to use beige buttons today or green buttons or whatever, or are we going to put the OK button to the left or the right or the cancel button? But in actual fact, that there's this machine hidden under the surface that the user has to try and understand. And I've got some finite state machines of like microwave ovens and one of a video recorder. And the video recorder's just got dozens of states and lines going everywhere. And it sort of makes it obvious why so many people's video recorders are flashing 12 o'clock, because the sequence you have to navigate your way through. In the same way that they had to find their way to Treasure Island, okay, it's a hidden finite state machine. They had to try and find their way through it. And most people don't bother reading the map or the documentation. They try and find their way through it. Okay, so that's a taste of Computer Science Unplugged. That's the kind of things we're on about. Always keen to hear ideas, things that you might have done as illustrations that worked really well, or activities, and also comments, anyone that's done some of these things or tried them out. And people always come up with new materials and new ideas for how to do them and so on. And we want to try and collect that together and make it available for general use. So, on that note, thank you very much for your time. And if you do want a copy of the book, email me and I'll get you a free one. PDF. Yeah.
Any questions? So this is really cool stuff. Are other people doing this kind of work for like math or chemistry and going to this extent to have basically a manual of?
Oh, okay. So are the maths and chemists and people making manuals and so on? There are, especially for physics and stuff, there are books about. There's a whole field called the public understanding of science, and there are journals of the public understanding of science and so on. But computer scientists tend to be too busy, sort of, doing stuff to write some of these things down. Yeah, but. There are, yeah, and there's also quite a bit of math stuff too. There's math websites and things like that. Yeah.
At what age, how young are the kids when they can sort of start to interact with this and understand?
How young are they when they can start to interact? Some of these activities I've done with like 4-year-olds, mainly just so that I can say I've done it with 4-year-olds. But so I've done quicksort with 4-year-olds. Okay. Because when you think about it, if you've got a bit of patience, what's required is not that hard if you've got someone who can cope with a few instructions. But I also use them like with my university classes, just as a 1-minute illustration, like maybe at the start or in the middle or something like that. And especially something like that, I can say, I've done this with 4-year-olds, so you guys, should have no problem with it. The age group that's really important for us to aim at is like 11, 12, 13, because that's when they're about to burn some bridges. Like they might decide that they hate math and they're just going to do well enough to get through in it. And so we want to get them excited at that age and think, yeah, that's what I want to do. I better get my math strong, that sort of thing. Yeah.
Thank you, Tim.
Okay, thank you.